Good morning, everyone. Welcome to room 1A and our first presenter, who is Hunter, I'm not going to say it wrong, Quintal, who is going to talk to us about staggered hazards and outdated floodplain maps that underestimate extreme flooding under future climate and land use change.
Good morning, everyone. Thank you for the introduction. As you said, my name is Hunter Quintal, and I am a master's student at UNC Chapel Hill, studying under Dr. Antonia Sebastian. And today we'll be talking about the possibility of the effect of floodplain being currently underestimating the extreme flooding that could occur under future climate and land use change. Flooding is an ever-present global concern and is often cited as the #1 costliest and #2 deadliest natural hazard. I'm sure everyone in this room recalls hurricanes Matthew and Florence in the last decade. And just in the last month, we've observed flooding impact the transportation network in North Carolina, displace and kill Australians in their capital city, and disrupt the operations at Disney World in Central Florida. I'm particularly interested in the floodplain fringe, which is the area just outside of the floodplain. And this area is considered to have a perceived lower risk than the floodplain itself, because there's no federal requirements for insurance, flood insurance to be in this exterior area. However, the floodplain fringe does receive flooding, and often this flooding can occur in a recurring period of time, as frequently as every year, such as in Sumter County, South Carolina. This is particularly concerning because the development that occurs within this floodplain fringe area exceeds that within the floodplain itself, and that can further exacerbate risks, including exposure and hazard, that can be even further exacerbated by extreme precipitation under future climate change. These two drivers of risk change, which is land use change and climate change, are what I'll be focusing this talk on across, and we'll be looking at different scales to better understand how this is changing in North Carolina. At the macro scale, we'll be looking at changes in discharge peak across the Neuse River Basin in eastern North Carolina. This watershed is home to 2.5 million people and is larger than the size of Connecticut and London combined. Particularly interesting is the increase in population, especially in the Raleigh area of the watershed, which is increasing by as much as 42% per decade. And this has incredible implications for land use change across the basin, and specifically the rate of land use change, which is a direct correlate of impervious surface cover, which has a strong control on hydrologic flows throughout the watershed, including reducing the ability of the watershed to store water and increasing the efficiency of the watershed to route water, which increases discharge peak as well as the volume for any given storm. Let's now look at historic changes that have occurred across the watershed. On the left, I'll direct you to a figure that shows changes in the volume of the 1% storm over the 20th century in Goldsboro, North Carolina. And what we see is an increase in the volume of the 1% storm by 33% over the last decade, or over the last century. And this is calculated using a 30-year moving window approach. On the right side of the screen, we observed the current display of land cover across, or land uses across the watershed. And we'll note that urban areas are primarily red, and forest and open lands are primarily greens, and forest and agriculture, and farmland and agricultural lands are primarily browns. If we then look at how different models project changes in both of these drivers of flood hazard, we can see an interesting story. In the left figure, we'll again see changes in the volume of the 1% storm, this time for the 21st century, and we'll note a gradual rise in the volume of that 1% storm. And on the right figure, we'll note that by the end of the 21st century, we'll have large expansions of urban sprawl, and we'll also have conversion of forest land into more farmland and industrial purposes. These two drivers will have strong implications for the hydrologic regime of the Neuse, and will allow us to answer a few questions, including: one, how will extreme rainfall and land cover influence discharge? Two, how will floodplain extent change over time? And three, will proposed buyouts reduce flood exposure? We'll answer the first question at the scale of the entire Neuse watershed, and we will answer the questions 2 and 3 at the scale of the city of Goldsboro. Goldsboro is an ideal study location to understand changes in flooding, not only because of its frequent history of experiencing flooding from recent storm events, but also due to its proximity to the Neuse River, which flows just to the southwest of the city, as well as 3 tributaries to the river, which flow through the city itself. In addition to these 2 characteristics, the city is also has 2 locations that are proposed buyout locations. These are identified as red stars in the map. And these buyout programs are government programs that enable the government to purchase land and remove people and buildings from the floodplain to effectively reduce exposure to a given storm event. And this will be particularly interesting for us because we'll be able to not only evaluate the change in exposure for a given buyout scenario, but also we can assess whether buyouts enable the reduction of future hazards. To answer the questions that we've laid out, we developed a model using VFlow, which is a physically based, spatially distributed hydrologic model that solves the kinematic wave approximation of the shallow water equations by routing water over land into in-channel cells and determining hydrographs at any location in the domain for a given hydrograph. The inputs to this model include a digital elevation model, land use data, soil data, and precipitation data to route water through the domain. And outputs from this model are used as inputs to a one-dimensional steady state hydraulic model, HECRAS, for each of the 3 tributaries that we showed on the last slide. The model is first calibrated against Hurricane Matthew and then validated against Hurricane Florence. And we'll note the difficulty that we had in calibrating Hurricane Matthew due to the complexity of upstream releases from Falls Dam Reservoir. So now that we've designed the model, we're able to consider the different scenarios that we'll be running through the model. On the left-hand side of the screen, you'll see the climate change only scenario where we increase the volume of the 1% storm. And we see that when we're increasing that volume, it is not spatially similar across the entire domain, and it increases relatively more in the upper basin near Raleigh, greater than anywhere else in the basin. Conversely, in the land use land cover change only scenario, on the right-hand side of the screen, we see impervious surface increasing disproportionately more with respect to the areas that are urbanizing greater, which is specifically Wilson, Kinston, and New Bern. And note that because this is a relative increase, we're not suggesting that New Bern is going to be more developed than Raleigh, and that Raleigh is the overwhelmingly more urban area. So if we then use these 2 scenarios as inputs to the hydrologic model that we developed, we can start to answer the first question that we posed, where we look at now changes in the discharge peak associated with those scenarios. And what we see in the climate change only scenario on the left-hand side of the screen is an increase in discharge peak much farther down in the watershed. Whereas in the land use land cover change only scenario on the right-hand side of the screen, we see increases in discharge are much closer to the areas that had a relatively greater increase in impervious surface area. If we then look at the combined scenario, where we consider climate change and land use change scenarios, we see nonlinear responses that we may not be able to well parse out if we didn't have this figure on the right to look at, which shows the percent increase in discharge peak relative to a 2020 baseline scenario. And that is the y-axis, and the left or the x-axis is the year of the, and this is decadal projections through the end of 2100 for each of the three scenarios that we ran: climate change only, land use land cover change only, and then the combined scenario. And what we find is that discharge peak responds proportionally greater to increases in changes in precipitation than it does to changes in impervious surface cover. And that in the combined scenario, we see synergistic effects where the combined scenario has responses, especially towards the end of the 21st century, that are greater than the additive effects of the first two scenarios by themselves. If we then scale, zoom into the city of Goldsboro, we can start to answer question number 2. And I was fortunate enough to receive funding by WRRI to develop a web-based tool that allows the user to toggle between the two different scenarios at a decadal time step through the end of the 21st century to evaluate property scale changes in flood hazard and exposure. And what we're showing in this image right here is the effective 100-year floodplain in blue, and then the effective 500-year floodplain in brown behind it. So if we take that 100-year effective floodplain and then map it and scale in a little bit more, we can start to parse out the 3 different tributaries to the Neuse River: the Little River to the west, Big Ditch, which runs through the center of Goldsboro, and Stony Creek running to the east of Goldsboro. Now, note that this is the effective floodplain, but we're not sure whether it's outdated or not. So it's useful as a base case scenario to compare against our future scenarios. And when we overlay all of our scenario floodplain extents, we start to see some interesting relationships that occur. In Big Ditch, we don't see any large spatial changes in the floodplain extent for any of the future scenarios that we ran. However, in Little River, we start to see an infilling of the floodplain between the effective floodplain extent in the hash mark and the 2020 floodplain extent that we projected in blue. So this suggests that there may already be some outdated floodplain maps within Goldsboro that are not accurately representing the hazards that are currently within the city. But within Little River, we don't see any large changes in the extent of the floodplain until the end of the 21st century. Whereas in Stony Creek on the eastern side of the city, we start to see some relatively greater changes earlier on in the scenarios that we ran. And this is likely due to a gently sloping topography in eastern Goldsboro as you transition into Stony Creek, which allows any increase in volume through the channel to result in a proportionally greater floodplain extent encroaching westward. Also interesting to note is the 2 proposed buyout locations that we discussed earlier. And these 2 locations are in West Goldsboro and South Goldsboro. And their purpose is to reduce flood exposure from the Neuse River floodplain, which they may be able to do as they overlap this effective floodplain extent. However, they're not significantly changing the floodplain extents that we're projecting in our figures, and that's because they're spatially distant from the 3 different domains that we were running our models for. However, it would be interesting to note whether a proposed buyout within the floodplain fringe, possibly along this dark blue and orange line of Stony Creek, may have some impact on reducing the future exposure and future hazards along the western side of Stony Creek, where there are a lot of buildings. We can then quantitatively analyze the changes that we were visually observing in the last slide by first looking at the figure on the left, which shows the aerial percent increase in the floodplain from a 2020 baseline condition. And we see that Big Ditch and Little River that we were discussing earlier had a relatively smaller increase in their floodplain extent relative to Stony Creek, which saw almost greater than 80% of its floodplain expanded. If we then you take an existing building inventory and overlay that on the floodplain extents that we're projecting, we're able to see very similar results where there are not many changes in the number of exposed buildings within Big Ditch and Little River. However, there's a 5-fold increase in the number of buildings exposed along Stony Creek. In summary, discharge trends are nonlinear in space, time, or with respect to future scenario. Rainfall exerts a stronger control on discharge than land cover. Buildings in gently sloping areas of the floodplain fringe are most at risk for future hazards. And proposed buyouts are better able to reduce exposure than they are hazards, at least in this model setup. I'd like to end on this slide where my next steps are to complete the website development and distribution that I was talking about earlier. While I'm finishing my master's degree right now, I'm staying at Carolina to do my PhD, and I'm looking for collaborators. So if any of this work is interesting to you, please reach out. I'd like to thank my sponsors, WRRI and the USGS, as well as my advisors, Dr. Sebastian, Drs. Dello and Dr. Sai at the NC Climate Office for their support over the last year. And I'd like to leave us on one quote from Dr. Miyuki Hino concerning the policy implications of this work. She found that for every one buyout that occurs, there are 10 new homes built within the floodplain. So if we're interested in using buyouts as a mitigation tool, we need to better understand whether or not they're offsetting these new drivers of flood hazard. And with that, I'll take questions. Thank you so much.
Make sure that you come to the microphone or I hand you the microphone so our online participants can hear you. Does anyone have any questions?
I'm interested if you looked at the more frequent storms rather than just the 1% storm, maybe the economic impacts of the 10% or the 5% storm. In many places, we're finding that the magnitude of the impact on urban infrastructure, on stormwater infrastructure and all is huge compared to when you look at the 1% storm.
Thank you for the question. That's a really good point that you make. For this study, we were more interested in overall changes in hydrology across the entire basin, and then scaled into a single city to address changes in the floodplain. For that, we only had time to this point to look at the 1% storm. I'm very interested in looking at even the 500-year storm, but also scaling it back to looking at much more frequent storms that are clearly happening, especially in Eastern North Carolina.
All right. Would you come to the microphone, please? Sorry. I'm sorry. That one wasn't on.
So I've missed how you modeled your land use land cover change.
So we were using existing data sets provided by the EPA. It's the Integrated Climate and Land Use
Okay.
scenarios, which we then had a statistical relationship to translate each land cover value into an impervious surface value and a roughness value that we use as inputs to the hydrologic model.
And you showed, were those catchment areas? Because you showed the land cover change and the 1% increase. Those were like sub-watershed?
Those were sub-watersheds, exactly.
What scale were those?
Those were Huck 10 scale.
Okay. All right. Thank you.
Yep.
I might have missed it, but what did you use to make the web-based tool, the one that was funded by WRRI?
Yeah, thank you for the question. I'm currently using RShiny, which is an application through the R programming language. And then we will be hosting it. I'm not entirely sure if it's going to be through UNC or NC State.
Thank you for this presentation. I was curious, I think there was a paper in Nature in January, maybe, that was suggesting for an analysis of the US as a whole, that the risk from future land use decisions, the risk of flooding is about 4 times what we'd expect the risk to be just from what we expect in climate change. I'm curious, I don't think that was distinguishing between increased impervious surface versus development moving into a floodplain. But I'm curious how do you think that that's result is not true for North Carolina, or it probably is true, and how it squares with your results?
Thank you for the question. I think flooding is an incredibly local problem. And so it's very difficult to make generalities across an entire country, for example. What we're finding even within the same city is that urbanization poses very significantly different results on even 3 different tributaries within that city. So it's really difficult to make that generality. And I guess we need to look more into it.
All right, let's thank Hunter for this really nice presentation. And we'll go on to our second speaker of the morning. We're going to pull that up. Our speaker is Madan Maharjan, and he's going to speak to us on the influence of big storms on the Black Creek Aquifer in Robeson County.
Good morning, everyone, and thank you for being here. So today I'm going to talk about influence of big storms on Black Creek Aquifer, Robeson County, North Carolina. So I'll be showing you some of our preliminary results, what we have been researching on. So let's start with what we know. This coastal aquifers extend across the Carolinas and Virginia, with slopes and thickens toward the southeast. And these are the confined aquifers, really productive and used as a primary aquifer in this region. One of them is the Black Creek Aquifer, which is most widely used in these areas. Groundwater flow is complex in this coastal aquifer system. Flow occurs laterally through aquifer, where recharge and this from the recharge to the discharge area, but also flow occurs vertically upward and downward in the recharge and discharge area, which makes it a little bit complicated. And also water level in this aquifer has been impacted by various reasons, definitely population growth, so need more water for the municipal use, overpumping for the by the industries and agriculture, and also flooding, which we have already hear about in the previous talk, which is going to be the new normal in this climate change. So we'll be seeing more frequent flood, and that would also impact these aquifers. So what we're trying to see here in this research is basically try to understand how the groundwater flow in this Black Creek Aquifer mainly, and also try to identify how much impact does these big storm have on the confined aquifer, especially when they are flooded for so long time. And here is a model in the left side where it shows that around the 10 counties nearby the Robeson County, which is my study area, there's about 50 inches of rain per year, and most of that evaporates back into the atmosphere, 32 inches, and it shows only 1 inch out of 50 goes to the confined aquifer, and rest goes out to the stream, back into the stream. So now we're thinking, okay, this is all right. So this been the past. Now in the new normal climate change scenario, when we have frequent flooding, frequent hurricanes, big storms coming in, would that still be valid? So that's what we're trying to understand here. And for that matter, we are using our 13 wells within the Robeson County. That's we have drilled starting 2017 and shown in dark blue dots in the map. and there are surface water.
I'm sorry to interrupt you. If you're moving
Oh.
your slides forward, we're not-
I don't know. So I was just moving in my slide here, then it was, okay, I'm sorry about that. Okay. I didn't realize. Thank you.
Okay. Should be good now.
Are we good?
Yeah.
Okay, so then should I start from the beginning then? Okay, I'm not gonna start from the beginning here. Okay, yeah. So this is the model which I was talking about on the left side. So just a quick review. 1 inch is just what that is recharging into the confined aquifers. And we're asking whether that is gonna be true in the new normal. So here's the study area. Now, I'm glad that I'll just look at there. So blue dots, those are the our study wells, 13 of them within the Robeson County. And the blue dots, light blue dots, where I collected surface water. And we also use a lot of resources from NCDQ and the surface, USGS, and one from the South Carolina well, just to see how the surrounding counties' water levels been changing. And you can also see perhaps this model, which is 3D, which basically shows the aquifers within that region. And all our wells are tapped and screened in the Black Creek Aquifer. And we can see that it's dipping southeast and it's thickening towards that. And these are not all the wells, but these are some of the representative wells. So here is our conceptual model. So what we conceptualize is basically recharge is taking place at the high grounds and discharging is the low ground as in the rivers or ultimately to the oceans. And primarily the horizontal flow is taking place throughout the aquifer. Whereas vertical flow is also possible where you have really thin confining layer as shown in the middle with a very thin layer of confined aquifer, or somewhere it's missing as well. Just like where the river cuts, especially you can see that Aquifer River has cut through that confined layer. Now it is really into the Black Creek Aquifer. Now also we are interested here looking at the flooding events. As I said, during the flood, water level, you can see that in the Lumber River and the Aquifer River, it rises up really high, up to tens of meters. And during those times, water flow or the hydraulic gradient in the stream reverse. So then we can think that, okay, now if that is reversed, then it's gonna create the induced infiltration, which could be contaminated with the lots of contamination on the surface and eventually get to the pumping wells eventually. Then one of the other things we have conceptualized that water chemistry would spatially and temporally vary. So to understand that, we collected a lot of data from those 13 wells within the Robeson County. I use symmetric loggers, which is shown in the left with a steel casing. So that's used in 13 of those wells and collected water level data every half an hour. And you can see that one right above that logger is a thermochron, which basically measures the temperature. And I have that in the 3, and which is basically shown in the next to that, the diagram where I have 2 loggers, one for barometric, one for the water level pressure, and the 3 black dots collecting the temperature data every hour. And so we collect those data every month from the field, and there is a student collecting the water level from those wells, verifying that what the sensors are reading is correct. And also I've shown water sample collection from those wells. And as I said earlier, I have been using a lot of DEQ and USGS resource to collect the water levels from the ground and the surface. So these hurricanes are not new, and you might have remember those. And these hurricanes really hit hard to the study areas, especially the Matthew and Florence. If you can see that these Matthew and Florence had dumped in respectively up to 15 inches and 30 inches roughly to the study area, but not so much by the Michael. So then what has it had impacted on the surface water? So we can see that surface water is rising really high during the Matthew and Florence, not a surprise. And also, but Michael and Dorian is not responding a lot because it's not dumping a lot of water in nearby or in that drainage basin. Just to give you a little insight, Lumber River has a smaller drainage area, whereas Aquifer is much more bigger. So there's a little bit lag time, but not much, but there are in between a lot of storms as well. So now what we are interested in here, and what I did basically was I looked at all the water level in those 13 wells and surrounding county wells and compare basically how the surface water and the groundwater compares, basically the hydrographs. Now I have 6 graphs here, A through F. So in all, you can see that blue line is running or hydrograph is there. That's basically the Lumber River at Lumberton. And I'm comparing that in the A with the surface water, surface aquifer, superficial aquifer. And as expected, there is a very good correlation between the two as expected. And now I'm looking into the groundwaters, confined aquifers at the Littlefield School, where I can see that there is a good correlation again with very little lag time and very little rise in the water level. But as you go down, now you can see that lag time increases and water level also, change in the water level also increase in those wells. It very much resemble with the surface water to some extent in the C, and then it plateaued. Now in the D, which is Alamac, next to very close to the Lumber River, when it's rising and falling limb, it's very much aligned with that. But after that, it just deviate. There's something to do that. If you're interested, I'm going to talk about that. I'm going to move on. Sammy Cox also shows very much similar, but with the lag time, this time it is 1.5 days with the water level change of 1.3 meters in that aquifer or in that well. Last one, you're seeing the black lines is wiggly lines, and which is basically due to the impact of the nearby pumping well. And you can see that during the rain event or the hurricane event, there is no pumping and water level is slowly rising up, and it's continuously rising because it was under, like the aquifer was depressed and it's rising up high later on as recovery. So we did the similar analysis with the 14 other wells within and surrounding the area. The wells are down below, the name of the wells, and we analyze water level rise in those wells. We correlate that water level with the Lumber River again, and also find out the lag time. So at the bottom, what we can see is a lot of the wells didn't show up much high water level rise except for Magnolia and McCain, but there is a pattern emerges out if you look at those blue, red, and orange color, which refers to Matthew, Florence, and Dorian. What we have found is basically average water level rise during Florence was the highest, followed by Matthew and Dorian. And similar thing with the correlation with the Lumber River, we can see the similar thing. There are some variation over there, but again, when we calculate the average correlation coefficient, we found that Florence had higher correlation with Lumber River with these hydrographs, followed by again Matthew and Dorian. Same with the lag time. This time there are very little lag time for a lot of the wells down there, which is basically 0, which is not really true. The 0 days, it is, so the resolution is dead. So it's not like 0 days, doesn't mean that it's right offset, but maybe there's some lag time, maybe some hours, which is not possible with the resolution of data I have. But again, a pattern emerges out when we looked at the average. Florence has the least lag time, followed by the Matthew and the Dorian. Now let's look at some of the water temperature. So as I showed you that I have using those thermochrons in some of the wells, and here are the 2 wells, one in the Prospect and one the Doc Henderson, which both of them are not very far from each other. I have 3 of them in the Prospect well and 4 in the Doc Henderson. So what we've seen, I have almost a year-long data from Prospect, and as expected, what we see here is as you go deeper into, the magnitude goes, amplitude go lower, and the lag time increases as you go deeper into the subsurface. And we are seeing here seasonal variation in the water temperature, and which is expected, and it's mainly because of the heat flow via conduction method. So I hope the similar thing is going on with the Doc Henderson in the long run, and with the more data, I would expect to see those. But Doc Henderson is still very interesting. If you looked at especially the one, Doc Henderson 1, which is the black line, there are two little dips around January, and one big dip around the February month. So also, if you looked at the sensors at the depth, so you can see that that dip goes decreasing as you go deeper into. And this is, I think, is a different phenomenon, and I can show you that in the little bit blow up here. So I'm looking at the precipitation event and looking at the water level change because of that, and also looking at how the temperature changes. Now, what I see here is whenever there is rain event occurred, water level rises as expected, but what is not expected was the how much groundwater temperature changed because of that, especially during the January and February, and mostly during the February month, where you have really dip. So I think that dip is basically the water getting into the well via the convection. So that's something different. And I think I have got only 1 minute. So I have here water chemistry, which is a lot of data. So I'm not going to go over here. I'm just going to say that especially and temporarily, these water shows that there are variations during the different times and in the space. I'll quickly show you that this one analysis, which I started doing, starting analyzing the anions, and in all, it seems like the chloride is the main anion, dominant anion, but the data I've collected from the Doc Henderson shows there's a big spike in nitrate, and it is the same well which shows that little dip in the groundwater temperature, and also that's the one which I don't have for the Mars because that area was completely flooded. So what I would like to say here is that's a take-home message. This Black Creek Aquifer is spatially and temporally varying in its water level and the chemistry, which are expected, but the degree of observed variation in some wells that could be indicating that these aquifers are not confined as we have thought, or maybe there are some things which is due to the human influence. So the future work, I'll keep on doing what I have collecting and try to analyze them to answer the same questions I had started with. And I would just like to thank all the people who had helped me and put together these research. So with that, I think I'm ready to take questions from you guys.
We can take a couple of questions.
Thank you for the presentation. I'm curious, I don't know if your data shows this, but looking at the recharge, I'm curious if you think about the ongoing total recharge of that aquifer.
Can you repeat ongoing what?
The ongoing total recharge of the aquifer over time. Do you get a sense from this data of how important hurricanes are for that, or are they a disproportionate share of that recharge?
So I think hurricanes definitely had a huge impact. As you can see here, Matthew, which dumped in about 15 inches, Florence, which dumped in about 30. So that has a correlation in the surface water for sure, but also in the groundwater, we are seeing a similar pattern here. The big one we are seeing here due to the Hurricane Florence. And right after that, if you can see that on the A, if you looked at in the middle, there's a little bump, and that is because of that Michael. So Michael didn't ran out a lot. So there is a little bit of that is taking place in the surface as well as in the groundwater, which you can see in the figure C, where you have a little uptick because of that Michael, but big jump because of that Florence. I think, yes, these hurricanes has disproportionate recharge to these aquifer, and that's what we are thinking as of now. And then that's the question we are trying to answer, whether that 1 inch recharge to the confine, is that still valid when we have so much of hurricanes coming back to back year after year, and when the water on the surface remaining for so long, which allows that to infiltrate into these aquifers. And most interestingly, Black Creek Aquifer, which is thought to be confined, which we argue that it is not. I can compare figure A and D, where the figure A shows with the red line is the surfacial aquifer, which totally resemble with the water level or hydrograph in the Lumber River, which is as expected. But the similar things is happening in the Alamac with the high level of water level rise up to 1.73 meters in that area. And then it's perfectly resembled the way it is showing with the Lumber River. And so we think that at least in some wells, there is good connection between the groundwater and surface water. And these have been disproportionately impacted by hurricanes.
One more question.
Tom Wilson, Avery County. We live, of course, in the Appalachian chain of mountains. Is there any studies going on the aquifers in that area? And as for your nutrients and that type of study, is that parts per billion or is that parts per million?
I have that report in parts per million, and matter of fact, what I have reported, that number is basically the conductivity, and which is not really the I'm showing the parts per million, but what I'm seeing is in parts per million, those numbers. I think I might be confusing you perhaps. So these numbers, what you see on the y-axis, are just basically microsiemens per centimeter, which is basically conductivity. And here I'm not really showing you the concentration, but these are proportionate to the concentration, but not the true values of concentration itself. But regarding your previous question related to whether there is some studies going on, well, I'm not sure. I have not looked into that round, but I'm sure that it is important and somebody is looking. I'm not sure.
Okay. Well, thank you very much. Great presentation. Of course, Avery County, we have 4 aquifers where it's where the Grandfather Mountain is the highest mountain in the Appalachian chain. And so we have 2, as the Continental Divide, we have 2 of our basins going into the Gulf, and then we have 2 basins going into the Atlantic. So it extends to Tennessee. So whenever you're going to look at research, I would reach out to the University of Tennessee also. Thank you.
Sure. Thank you.
Let's thank our speaker. Our next presenter is Curtis Weaver, and he's going to speak to us about the magnitude and frequency of floods for rural streams in North Carolina, South Carolina, and Georgia.
So good morning. Thank you for the introduction. Yes, my name is Curtis Weaver. I'm with the U.S. Geological Survey, the USGS South Atlantic Water Science Center, and I'm based out of the Raleigh office. I'm here this morning to share some information about a flood frequency study that we are in the process of actually wrapping up. It's a 4-year study that's coming to completion here in the next, within the next coming months. I want to acknowledge my partners in crime here. Here is a team of folks that have come together to complete this study. We did this previously the first time in the mid 2000s based on data through 2006. And so we had the opportunity to repeat it beginning in 2017. If the USGS is known, one of the things that the USGS is known for, of course, is the stream gauging network. And what you have in front of you is a snapshot taken earlier this week of the USGS National Water Dashboard. It's a new online product showing real-time conditions in the terms of the background percentile statistics for this time of the year. So we have quite a number of stream gauges across the three centers, across the three states, over 900. But Murphy's Law is always present, even in hydrology. And as my former supervisor, Gene Robbins, sitting over here, will attest, we get phone calls. There's always the need for information at a point where you don't have data. So even if you have lots of data, somehow, some way, the phone call that comes in is, we need data at this particular location where you don't have data. And so that is the benefit of being able to do a flood frequency study, not only for gauge sites, but for ungauged locations. So USGS has historically completed these kind of studies from time to time. In general, we try to do an update every 10 years. Truth be told, it's probably 10-ish to 20 plus. Sometimes here in North Carolina, we have stuck pretty close to the 10-year cycle. But if you look across the country, that cycle varies. So we began this study by doing the at-site flood frequency statistics using the PeakFQ software. Some of you may be familiar with that software. You may have used it previously. And then as of now, the current PeakFQ software is based on the Bulletin 17C techniques. And these are techniques, these are federally recognized techniques for flood frequency analysis across the country. They superseded Bulletin 17B a few years ago, and Bulletin 17B was released in the mid-1980s. So this was a pretty long stretch between the time that the techniques were reviewed and updated. Again, when you have ungauged locations, we develop statistical relations to allow folks to be able to estimate the flood frequency statistics at ungauged locations. And then we take those techniques, as of the past 10 to 15 years, we take those techniques and we put them into StreamStats application. That is another application some of you may have used before, where you can go pull up a map, find a stream of interest, click it, and get a basin delineation, basin characteristics. And then the current techniques are built into the StreamStats application that we have now. In other words, the previous study, those techniques are built into the application as of today. So one of the things that we have sort of struggled with over time is the issue of flood recurrence intervals versus AEP. And in the previous study, we did start trying to be a little bit more focused on saying AEP as opposed to recurrence interval. But in short, really the AEP is the inverse, if I can do this without being too shaky, the inverse of the recurrence interval. So if you have a 10-year flood, if we stand here and talk about a 10-year flood, then we're talking about a storm that in any given year, there is a 0.1 or a 10% chance of being exceeded. But what happens is a lot of times folks will misinterpret recurrence intervals, and they'll say, well, it only occurs once every so often. Well, that's not the case. And so what we have to try to do is to steer the thought process to being the probability of something being equaled or exceeded on average a given number of times within a period. So if I use this example graph in front, this is for a site in South Carolina. You can see a 79-year period of record indicated by the blue bars. And then the yellow, the orange line is the 10% storm. So we can look at this and see that there are 8 peaks, there are 8 annual peaks in this period of record that exceeded the 10% storm. So on average, there was one exceedance every 10 years, but that doesn't mean that it occurs once every 10 years. If we look at it a little closer, where those peaks occurred, we can see that the actual length of time between those peaks range from two up to 20 years. But again, we say on average in the 79-year period of record, 79 years divided by 8 is about 9.9. So again, on average. So just a little bit of a sidebar there to think about when we talk about AEP versus recurrence interval. So at site for this current study, at site flood frequency statistics were computed for 964 unregulated gauges. Here's the breakdown by state. In addition to the 3 states, that is North Carolina, South Carolina, Georgia, we had 4 additional states where the river basins were overlapping. Of those 964 sites, there were 335 that were active as of 2017 and had 30 more years of record. And when we look at those tests, and we did a Kendall's tau trend test, we see that 83% did not display a statistically significant trend, whereas 14% had a downward trend and 3% had an upward trend. And I'm not going to dwell on that too much because my colleague, Tony Gotvald, will be following this presentation with a little bit more focus on the trends from this study. So one of the other things that we look for in a statistical analysis is to take out the gauges that are redundant. What do we mean by gauges that are redundant? We're talking about when you have a stream flow network and some gauges are nested within larger basins where you have data, or you have ratios, gauges that are within a realm of ratios, drainage area ratios, or you have overlapping records. And so there is a concept of redundancy that is part of looking at your data and reviewing your data. So we completed some redundancy tests and took out 163 of those 964, and that left us with 801. So here we are near the end, ready for the regression analysis. We have 801 sites. And when you do a regression analysis, the more sites you have, the stronger your relationship is likely. Again, I say likely to be. And so you can see from the chart that North Carolina and Georgia carried the load of the sites that are in this regression analysis. Looking a little closer, looking at the distribution for the period of record, we had 52% of our sites were periods of record less than 30 years, and then 23.2 and 25% 30 to 50 years and greater than 50 years respectively. USGS considers a period of record at 30 years or more as long-term. Now, 30 years, granted, is not a lot of record, but that is the threshold at which we consider a long-term record for a site. So ordinary least squares is used we used ordinary least squares to do some initial exploratory analysis between the statistics. And we had a list of 26 basin characteristics. We also completed tests to make sure that there was no high correlation among the 26 basin characteristics themselves. You don't have characteristics that are highly correlated with each other. We used a period of record through 2017, but we also went back to 2018 for a small group of sites in North Carolina and South Carolina that were impacted by Hurricane Florence. So when Hurricane Florence happened, if the stream gauge attained a peak discharge that was in the top 5 for the period of record, we went back and picked up that record as far as this analysis. For flood frequency, the Skew value is a very critical value, and with varying lengths of record among your stations, you'll have a wide variation, likewise in Skew values. And so one of the steps that is taken in a flood frequency study is to do what we call a regional skew update. Basically, develop a regional skew that is then weighted with the at-site station skew in the end for the flood frequency statistics. It sort of helps to tame, if you will, the wild variation in the skew statistics that occur, again, primarily because of period of record lengths, the variation of period of record lengths among the sites. And here is the list of basin characteristics. I won't go through these, but we had your 11 physical characteristics, drainage area being one of the most recognized. Down at the bottom, you'll see ecoregions characteristics. We defined hydrologic regions using the EPA level 3 ecoregions as well as the Sandhills EPA ecoregion. That is a level 4 in the EPA system. And again, some land cover characteristics as well as some climate characteristics, and then soils characteristics that we put together for the basins, for the regression analyses. So in the end, the variables that were statistically significant were the drainage area and then the percent of the basin within the hydrologic regions. And of course, when you see the list here, you say regions 1, 2, 3, 4, and 5. What does that mean? It corresponds to the Piedmont Blue Ridge, the Sandhills Coastal Plain, and then there's a 5th region in southern Georgia. There was also a cross product of the drainage area, the drainage area and the percent of the Blue Ridge Basin. And I'll explain that in just a second here with this graph. So here is how the regression equations plot. If these are 5 regions here, they're very similar in slope, except for the Blue Ridge, which is the dark blue. And again, based on the data and how that plotted out, there was a steeper slope for the regression equation in the Blue Ridge, and therefore the cross product was used to reflect that in the final equations. For the range of values here at the bottom, you can see the drainage area, for example, hydrologic region 1, which is a Piedmont, ranges from 0.08, I'm having trouble reading myself here, up to 8,900 square miles. So again, it was a large range in drainage area that these equations can be applied to. If we take them and compare them to the regression equations from the previous study, really not a lot of change other than a little bit of change for the Sandhills, which is the light blue at the bottom, and the Blue Ridge, which is again the dark blue. That's attributed to picking up a few more gauging stations with lower drainage areas, and particularly for the Sandhills. Sandhills is not a very large region to begin with, so you don't have to add many more stream gauges to change the slope of your regression equation. Similarly, for the this here, I apologize, was the 10% AEP. So these were the regression equations for the 10% storm, and then for the 1% storm, we likewise had similar comparisons, very strong between the current and the previous study. For stream gauges with 30+ years, we pulled those out and we took the mean to compare the final weighted statistics between the current study and the previous study. We took the mean of the 10%, the 1%, and the 0.2% flows, took the mean of those, and likewise took the mean of the flows from the previous study. And so we find that 62% of the updated, for 62% of the sites, the updated statistics are within 10% of the previous study, 23% increased by more than 10%. And then there was 15% that decreased by more than 10%. And one of the things I want to point out on this on this map. If you look here in the coastal plain, you see a lot of red triangles indicating increased, based on the legend, increased flood frequency statistics. And so this sort of echoes the occurrences of Matthew and Florence. We did have a lot of increased flood frequency statistics at the gauges in the coastal plain following those two events. So I would like to stand here and tell you that we are within a month of publishing this, publishing the report. But an email was received in early December saying that there have been some issues identified with the PKFQ software. And so there's some minor issues with the PKFQ code that are currently under investigation. One of the primary issues has to deal with the method of the computational method of the mean square error for the at-site skews when it's weighed with the regional skews. This is, imagine standing at the finish line and you're ready to turn in your report to your teacher. And you get an email saying, hold up, and we've got some issues to explore. So I will let you know that there is some investigation currently underway to look at some errors in the current PKFQ software. The good news for our three-state area is that the effects may be minimal because the at-site skews that we had were not within the ranges of concern identified by the team that's having to investigate. This not only affects the PKFQ software, it affects the software that the Corps uses for their flood frequency analysis. So we are currently waiting for a new PKFQ to be released. And when that happens, we're going to do some verification checks and final confirmation before we finally publish the report. USGS has just released a page that has some information about this. If you're interested, there is a QR code on the screen in front of you. If you want to grab that, if you can, I'm not sure how well from where you're sitting, but again, this is kind of an unfolding situation at the moment. We're waiting to resolve this and then get back on track to complete this study. So I'm going to stop and say if there's any questions, or you can catch me on the side afterwards. One of the things that you look for in statistical analysis is to come up with a good equation that's relatively easy to use, that does not have variables that are hard to define or to delineate. Of course, we put our equations in StreamStats, so that sort of takes care of it for you. But that said, you do want to have an equation that's very easy, somewhat easy to use and reasonably within reason to be able to apply. Thank you.
So let's thank Curtis, and we'll go straight on to our next presentation from Anthony Gotvald, who's going to talk to us about the statistical analysis of these data.
All right, can you hear me? Sorry about that. I was having a little.
Yes.
Can you hear me? Okay.
And if I could let you know one thing real quick, at the top of your screen, your share screen is showing presenter view. If you click on.
All right.
Let me double check.
So you can't see my screen?
We do see it is just showing your presenter view. No, I'm sorry. No. Yeah, it's showing your presenter view.
All right, let's see here. That worked.
No, sorry. Let me double check. Should be at the top. If you're seeing it at the very top, it should on your view options.
Let me try this again. Yeah, because we had it working before.
Had it before, yeah.
All right, is that
There we, that's better. Great.
okay? Sorry about that. All right. All right. Good morning, everybody. My name's Tony Gotvald. I work with the USGS in the Norcross, Georgia office. We're part of the South Atlantic Water Science Center that makes up the states of Georgia, North Carolina, South Carolina. So my title is Surface Water Specialist, and so I give technical guidance on surface water activities for the 3 states. Today, I'm going to give a presentation about the trend analysis that Curtis had mentioned in his previous presentation that we did as part of this flood frequency study. So I was going to go in a little more detail about that. All right, so let me grab this here. All right, and just to recap, like Curtis had mentioned, we did a study in 2009, and then this update that's in the works right now. And so for this update, we had 964 sites, and this just showing that distribution. So for each of these sites, you know, what our underlying data that we use to compute the at-site flood frequency statistics is the annual peak flow for each water year. So just an example here. If you look here, this is the 2017 water year. So the water year starts October 1st, 2016, the end of September 2017. So we have this continuous discharge data that we collect at the site, and we take the largest instantaneous discharge value for that given water year, and we compile that, and that's called our annual peak stream flow. So as we have these long-term gauges that long-term being 30 years or more is usually what USGS designates as long-term. We sorry, it slid. So, you know, we collect this data, or compile these annual peaks, and that's used to compute the flood frequency statistics. So we take those annual peaks using the PeakFQ software and fit a log Pearson type 3 distribution to these annual peak flows to compute the statistics. But as part of that, we're assuming stationarity of these annual peak flows. So we assess that using the Kendall's tau test to see if there's any significant trends in the data. And that's part of the PeakFQ software does the Kendall's tau computations and gives you the results of that. And then we analyze that. And so I'll go over some of the results there. So just going back to this Tar River at Tarboro, this long term, we had 120 peaks here, and then you see Hurricane Floyd here. Here's Hurricane Matthew. But overall, what we assess with that Kendall's tau is we have this tau value. So if it's negative, there's a decreasing trend. But you know, if the p values for this study, if it was 0.05 or lower, we consider that significant. So here we have a high p value. So you know, there is a slight negative trend here, but it's not significant. You know, for the 120 years of record available here. And so this Kendall tau test can be sensitive. The shorter the record that you have, and then if you have a wetter period at the beginning and a drier at the end, you might see significant results that just may be due to the cycling of wet and dry weather. And so here, just show an example where we took a subset, or I took a subset, just taking 64 years of that record in the middle there, where I took where you have this wetter period here, dry here. You see a significant downward trend here. So that's where we assess more, looking at the longer term sites to assess these trends, because you might see a significant trend in a shorter term record, and it just might be cycling with wetter and drier season or years there. So here was just to illustrate that. And then to illustrate where you can see a significant upward trend here on the Red River in North Dakota is a place within the US that there has been significant upward trends in the annual peak flows. And just to illustrate that, I show this, there's almost 140 years of record here, and it's showing there was some, flood events here, and then you had this dry period, but fairly recently you see more and more larger annual peak flows occurring here. And so this results in a significant upward trend. And like I mentioned, we want to focus more on assessing the sites with a longer term record. So we took all the stream gauges with 30 or more years of record that are currently operating. So we had annual peaks up to 2017. And like Curtis mentioned before, there's a few that had peaks in 2018 from Hurricane Matthew that we included. But overall, most of these were up to 2017 water year. So looking at all the ones with 30 or more years of record, this just shows the downward red triangles means a significant downward trend, and then the blue upward is significant upward trend, and then the black dots is no significant trend. So you can see, just looking spatially overall, you see a lot more significant downward trends than upward. There's some upward scattered about, but you do see a lot of downward, a lot more than upward. But then, there's many more that aren't significant. And then, looking at the longer term record, so taking those stream gauges and then any that had 50 or more years of record, so anything between 30 and 49 drop out years of record, then you see, those significant downward trends still, and there's a few upward. And looking at 70 or more years of record, you start, seeing this pattern here where there's a lot of significant downward trends in this area. And then you go to 90 years and you can see, still see those here, but looking at the 70, there's some upward here. There's one here, a couple in Virginia. So let's look at some of these. There's a couple downward trends here in North Carolina, ones and then upward. So let's look at those. But first, here's just breaking it up to showing, the percentage of the stream gauges where we saw that had 30 more years of record that we saw upward trends was, usually less than 4%, as we look at 30, 50 and less than 14% upward. So you do see more, not a large percentage, but you see more downward trends than upward trends. And it seems to be fairly stable no matter, how long the period of record is. So looking at some of the North Carolina sites that were showing trends, here's showing the French Broad River in Asheville. So this one here. So at the time we did the study up to the 2017 water year, it showed a significant trend. The p-value was downward trend, a little less than 0.05. But what I did is I took, since this study, we've had annual peaks, for the 2018, 19, 20, and 21 water years. So these four, when I add those in and do a trend test, since these are a little higher than what's been the last few years, that downward trend actually is no longer significant with the p-value of 1.23. So even with long-term gauges, as you collect more data, there's possible cycling going on. And so that's when it's important to, look at the gauges with the longest period of record to assess trends. And just to point out too, these are all rural stream gauges that, Curtis mentioned. So there's no impervious area, high percentage or development. We consider for the study, any stream gauges where there's less than 10% impervious area in the watershed that's considered rural. So, we're not looking, this is looking more at natural streams. So adding those 4 years of additional record, then that significant trend, downward trend is no longer significant. And then just looking at another nearby site where there wasn't, a significant trend. I mean, they're showing a downward trend in this area, but it's not significant in this area. Then looking at the Deep River, here, this other site that was showing a downward trend up to 2017 data, it was the p-value 0.023. For this one as well, the last 4 years had higher annual peaks. And so by adding those in, that trend, downward trends no longer significant. So basically with the additional record we have now, since 2017, these drop out. So, the majority of the state here, in North Carolina, you're not seeing significant, trends in the annual peak stream flow in the stream gauges in North Carolina. And then looking at this one, Northeast Cape Fear River here, this is a case showing, so we have 78 years of record. So not as quite, the other ones were, had 100 or more years of record or just at 100. So this is a slightly shorter record, but it was showing a significant upward trend at the time of the study. And this was using data up to 2018. It was just at that 0.05 p-value. And then when I add 2019, 20, and 21, there's still an upward trend, and it's even more. The p-value is lower, so it's still upward significant trend. So, we'll assess that further as we do these studies and look. But in this case, that this record started later on than the other ones. It's a shorter record, and there was a lot of larger events in the early 20th century. So, there might be some larger events here that weren't captured at this stage that might, offset that significant trend we're seeing upward. And then looking at, this area here where we're seeing a lot of downward significant trends. So here's one in Georgia. And what we saw for these stream gauges in this area, it's the case where we had a lot of large historic floods. And then there was drought years here where we didn't see as large as floods. And so that was causing this significant, downward trend. And so it's a wet, here's where you have those extremes on both ends where the Kendall's towel can be sensitive to that, where you have, higher floods at one end of the period and then drier at the other. And so that's the case here where it could be cycling going on. And that's something, we'll monitor, assess each time we do the study as we collect more data and see, if these trends are still showing up significantly downward. And then here, looking in this area down here where we're seeing significant upward trends, this is another case where we're adding the additional data collected since we did these trends assessments for the study, adding a few more years than that. These trends here aren't showing up as significant because they were just barely under the p-value. And this is a case where we had some hurricanes coming through here. So we had some larger flood events later on where it was drier at the beginning of the record. And so in summary, this, there wasn't, as part of this study there, we didn't do a comprehensive analysis of the causes of the trends. That was out of the scope of the report. We were just assessing and documenting them. And so based on, the observed significant trends that we saw in this study, we felt they were more than likely to cause the result of wet and dry cycles. So it's making it unsure if these trends, will continue in the future. So, as we collect 10 more years of data and update the study again, we'll continue to assess this. And just due to the lack of strong and consistent statistical evidence of significant long-term regional peak flow trends throughout this area, we just maintained the traditional assumption of stationarity for this study and we didn't do any adjustments for trends. And then the last bullet one, for this study, we assumed that the annual peaks were independent of each other when we did the Kendall's towel, and we didn't evaluate the existence of long-term or made the assumption that there's long-term or short-term persistence. But usually if you assume that the annual peaks are independent of each other, then that tends to overestimate the number of significant trends. So by evaluating long-term and short-term persistence and using those assumptions, there would be more likely less significant trends. And so we plan to do that. The next time we do the update is to go more in depth of assessing that. We just, for this study, we didn't see a lot of significant trends, and so we didn't evaluate further, but we plan to next time. There's a methodology in place recently with the USGS has been using to start assessing this persistence, long-term and short-term more. So we'll plan to do that for the next update. So that's my last slide. So if there's any questions.
Do we have any questions?
Hi, my name is Keith from Lenore Ryan University, and I'm going to ask a question out of complete ignorance, not out of any expertise. And I'm curious about your rural testing sites, and if you looked at if you did any spatial analysis of upstream and downstream of more urban areas, and if that showed any differences. Thanks.
No, yeah, we just focused for this study on rural stream gauges. We are planning to do a study on urban stream gauges, so we'll assess, go into further detail on trend analysis on those as well. But for this study, we solely focus just on the rural stream gauges and did trend analysis on the stream gauges that we're planning to use to develop the regional regression equations.
Marshall Taylor. So does that mean that the regressions built in the stream stats are based on the old studies only?
So as we update, the idea is to update these studies every 10 years as we collect 10 more years of data. And so when we do the update, then the most recent equations will be implemented in stream stats. And that's the case where the study Curtis was talking about. And, once we get those equations approved, we're just waiting to do some verification with the PKFQ results to ensure that, those issues they found don't impact us. Once we get those.
Let me clarify. The urban regressions built in stream stats are based on old studies, the prior studies only?
Yeah, so there was a study done in 2014 for urban stream gauges, and those are incorporated into stream stats. And so we're getting to that point now, where we have 10 years of additional data, and we're working on getting funding to update that and the urban one. And once that's done, we'll incorporate those updated equations into stream stats. Does that answer your question?
He said yes.
Okay.
All right, let's thank Tony and all of our speakers. I think we have a break now. Thank you all for participating in this session.
I need to make just a quick little change to one of
Sure.
our presentations once you get it on the
Yeah,
desktop.
no problem. And they should all be, I'm sorry, which one?
I'm
is it?
virtual, sorry.
Okay.
Yeah.
So I already had that one up. Okay, great.
Thanks.